Mm. Of that. So real-time transformer, this is the real-time version of the object detector. And their title of the paper is like this, and that's published in Baidu in CVPR, which is the top conference in computer vision field, 2024. Okay. But I mean, their algorithm is having some component which is beyond the scope of this lecture. So I will give you very brief, uh, I mean conceptual features how they could make their algorithm real time here. Okay. So compared to a recent version of the YOLO, they are saying that their algorithm is faster. The x-axis, they are showing the millisecond speed. Okay. And if it goes to this direction, that it means the algorithm is faster, takes less time. And this y-axis is denoting the accuracy, and their RTDTR, their performance lies in here. Okay, so their algorithm is more robust in accuracy and faster than previous YOLO-based algorithms. And the main motivation for this RTDTR is the multi-scale features are helpful for improving the performance of the object detection algorithm because, as I told you in previous lecture, in images there could be lots of uh, size in the same object. Okay, some people can be like this size, and some people could be larger in size. Okay, in the same, even in the same image, we can have many objects that is in the different scale. So, I mean, using different kind of, uh, filter size for the CNNs, we have to somehow capture the humans properly. Okay, so we have to capture it in multi-scale. We have to make the features in the multi-scale as well. So RTDTR is considering that, but the original DTR is not having such schemes. So we extract the resonant features first and using that as the input to the encoder decoder composed of the transformer architecture and map it to bounding box and class probability in DTR. So there's no consideration for the multi-scale list, but RTDTR wanting to capture multi-scale objects and also but there's a trade-off between these two. If we extract multi-scale features, for example, if we want to capture three levels of features, that means we may have to get third, three times time complexity. So to generating three scale features that normally means we may take three times time complexity. So normally multi-scale features are not helpful for securing the real-time speed. Okay, there's some trade-off between these two. But RTDTR, they somehow wanting to well trade off between these two. Okay. And the other important motivation is in DETR, we have both encoder and decoder of the transformers, but they observed that encoder, they are accounting for almost half of the overall uh, G flops, which means the time complexity. It is meaning that in overall time for the DETR, encoder takes almost half and decoder takes almost half, remaining half. Okay, but the encoder contribute only 11% of AP, which means the accuracy, in deformable DTR, which is the one variant of DTR. Okay, so deformable DTR, as far as I remember, it's published in ICLR 21, and the original DTR was published in ECCB 2020. So more advanced version of DTR. But anyways, the encoder was not effective in DTR architecture. They, by experiment, they revealed that the encoders are not very helpful for improving the accuracy. But even though their contribution in low contribution in the accuracy, they are saying that the encoder takes a lot of time, almost half of the overall time complexity. So in RTDTR, their main component is uh, developing some efficient encoder. So in here, you have a transformer-like encoder, right? But they are having less, actually, I mean, less number of, how to say, uh, I mean, what to say, less number of tokens compared to the original DETR. Okay, and by it is achieved by reducing the, how to say, this 2D two-dimensional feature space. And also, after doing some AI-FI, which is similar to previous transformers encoder architecture, they are having CCFM modules. They are somehow fuse the features obtained from previous AI-FI. So AI-FI, that's the intra-scale feature interaction module, and the CCFM, which is called as cross-scale feature fusion modules. So their idea is, um, I mean, they want to have multi-scale needs, okay, but having a self-attention mechanism on all of the multi-scale features are inefficient. It may result in almost 3 times time complexity. So their motivation is they extract the multi-scale features, which is in the 2D space, okay? And let's say S3 is the largest scaled image feature. So from the image, we extract 3 scaled image feature, and the largest one is called as S3, and the next largest is called as S4, and next the smallest is called as S5. Okay, so this is as far as I remember, this backbone is also the CNN architecture, and this S3, S4, S5 is the layer, certain layer of this CNN network. And you may ask why there's no S1, SS2. That's too big, and they are too early layers of the CNN, so they cannot capture any semantic meaning yet. So they are using some layers after S3. Okay, that's the reason. Okay. And also S3, that's already reduced version of the original image. So, I mean, this is also helpful for reducing the time complexity. And they apply AIFI, which is the attention-based, I mean, architecture transformer, which is similar to transformers encoder architecture, but they only use S5, which is the smallest feature. Okay, they only use S5 to obtain to apply the attention mechanism. Okay, I mean, this may have less token, okay, compared to S4 or S5. Okay, so this is one reason why their encoder is becoming faster, becoming efficient than original DTR. So, I mean, when the number of input to the transformer encoder, their token number, their input number is n. The attention mechanism, their time complexity is order n scale, right? So because of this, reducing the number of n is helpful for reducing the overall time taken for the encoder. Are you guys understanding this? Okay. So they only apply attention mechanism for the smallest uh, resolutional two-dimensional feature. Okay. And they get improved features after the attention mechanism. Okay. And then they involve the CCFM module, which fuse the features of different scales, which means they are using CNN-based architecture, which is the CCFM, to merge the information within these larger scale 2D features. Okay. Are you guys understanding this? They only apply attention mechanism, which is have the highest time complexity for smallest image feature, and then apply CNN-based operation to fuse the remaining scales information. Okay, so I mean this is the improved feature for the smallest feature, and they are combined with the larger scale features using the MLP, the CNN uh, operation, which is simpler compared to the attention mechanism. And all of their information is concatenated afterwards. Okay. Are you guys understanding this? Okay. Their high level concept is applying attention on, the smallest 2D features and combining the multi-scale needs using the CNN operation, which is simpler. And this is the final, uh, I mean, feature that is outputted from the encoder. Okay, so this encoder is becoming efficient thanks to this kind of thing. Okay, and also they can encode multi-scale needs anyways using the CCFM module, but also having the attention mechanism for the minimal scaled E2D features. And also after that, they are having this kind of query selection uh, mechanism after obtaining the initial query from the encoder before, feeding this query, which is the output of the encoder, to the decoder directly. They are having the mechanism that select the queries. We call this encoder output, which is the input, decoder input as the query. Okay, we record this as query. Okay? From each entries of the encoder output, we select something which may have more information than others. And also decoder, their time complexity is order n scale when their query number is n. So by selecting better, input to the decoder, they can also accelerate the decoder speed as well. Okay, so this query selection, to understand this properly, you have to understand the deformable DTR, which is advanced version of DTR. But this is beyond the scope of this lecture. So you, at this moment, you can think that, anyways, you can filter out unnecessary decoder input, and by doing that, you can also accelerate the decoder. Okay, so this is the conceptual things that this RTD-ETR achieved. Okay, so for the importance message here is, multi-scale features are incorporated in the RTDTR, but by applying the small scale features via attention and combining the larger scale features using CNN operation, which is efficient. So encoder becomes efficient, and by doing that, the overall DTR becomes faster, and also by sampling the decoder input, okay, we can also accelerate the decoder, and by this kind of using this kind of tricks, we can secure the real-time DTR. Okay. And this is the real-time the RTDTR, and you can see their FPS frame per second is very high, even compared to the YOLO algorithms. This algorithm is very fast. And at the same time, their accuracy, this is the main accuracy, is becoming also even higher than the DTR variant. So this is the original DTR, but these are some other DTR variant which advances this DTR in many aspects. Okay, but even compared to their DTR variant, this RT-DTR is also very fast and very robust. And their paper is published in last year's CVPR. And if you are interested in studying this RT-DTR, then read their paper. And also the code is available. Okay, this is end of the efficient object detection algorithm. And now the new topic is the training techniques. Right? So once I explained about there are some more optimizers called as ADA-GRAD or RMS probe or ADAM. So we are normally using the SGD, which is the stochastic gradient descent algorithm. But there are some variants to SGD that advances this SGD in multiple aspects. So in this lecture, we will learn about that. Okay. And I think this method can be helpful for, doing your assignments as well. Okay. Maybe assignment 2. So this is already you are familiar with. So to be used in the deep learning, overall deep learning architecture, each layer have to be differentiable. And differentiability, that means two things. Their output should be differentiable respect to their input. And their parameters, if one layer have a parameter sector, then their parameter have to be differentiable respect to their output should be differentiable respect to their parameter. Okay, that's the two essential condition that the one layer on an arbitrary layer could be used in the deep architecture. And for that is because we always have to get this DLD sector for all the layers inside the overall deep network, okay? And for obtaining this DLD sector, L should be differentiable for every layer's parameters, okay? For obtaining that via chain rule, every layer have to have these two things, okay? That's the thing what we have learned before the midterm. Okay. And any differentiable layers could be in between this input and output. Okay. But CNNs, their convolutional operation is differentiable and they are widely used in processing the image signal. So using convolutional layers, we could make this type of architectures, which is deep in layers. Okay, that is called as CNN. And using the PyTorch, I mentioned that we can define we can stack multiple differentiable CNN layers and constitute the CNN operation like this. And using the PyTorch, using this training code, we can train all the deep architecture. Okay, that's the thing we have learned. And we learned that we can use gradient descent, okay, to optimize the parameter sector, okay, using the DLD sector, right? We learned that we can optimize the parameters, okay? And we also learned about the difference between stochastic gradient descent and gradient descent, okay? Gradient descent, we optimize the overall parameter by seeing all the training data, but SGD, we see the samples in mini batches and update multiple times after seeing each unit, okay? But in practice, this is GD and this is SGD. I mean, GD, you may think that GD produce better result because it goes one optimal steps. Okay, after seeing the training data, all the training data, it goes to one optimal step. But that optimal step is optimal in the aspect of the training data, but we are testing our network for the unseen testing data. So getting optimal parameters for the training data is not always optimal for getting good parameters for the unseen testing data. So because of that, stochastic gradient descent, even though it goes random steps and in the aspect of the training data, it may seem non-optimal, okay, for some cases. But in practice, this SGD, thanks to the randomness, it can produce better result than the GD multiple times, okay? We already learned about that. Yeah. Uh, but I mean, now this is the new thing, momentum. So when using only this type of thing, um, when this becomes zero, let's think about this kind of situation. So when the initial um, parameter sector is here in x-axis, uh, we start from here, let's assume like that, and this is the error function, okay? So error function or loss, okay? So we always want to minimize the loss. We always wanting to secure the sector which can minimize the loss, entire loss L, which is the difference between ground truth and our prediction. So this would be our optimal parameter sector. Are you guys agree with this? Okay. And by iteratively applying this kind of formula, we always find the slope at this moment, and that would be this. Okay. I mean, originally the slope like this, but there's minus, so that slope would be direct this way, and multiply small scale to this direction, we are updating our parameters slightly. Okay, that is how this algorithm is working. But thing is, let's think about this point, this yellow point. At that point, DL dissector becomes zero. Are you guys understanding this? So at this moment, the slope, this graph's slope is DL dissector, and at this point, DL dissector, that is going towards zero. Are you guys understanding this? Okay. And then it can immediately stop there because using this formula, if there this DL dissector is becoming exactly zero, then using this formula, sector nu is entire, forever, this becomes zero. There's no way to escape from this point that is having exact zero values for DLD sector. Are you guys understanding this? Okay. So, if it reaches exactly this point that their DLD sector is zero, then somehow that optimizer is stopping there forever, and we cannot reach this type of best parameters. Okay? We cannot reach here, which is the best parameter. Okay, are you guys understanding this? And there are multiple, we call this type of things as the local minima, where first order gradient is zero, okay? But here also the L dissector is zero, but actually their L value is minimum in global sense. So that they are called as global minimum, okay? This is the one global minimum, but all others, uh, their first order gradient is zero, but so there's high probability that their optimization stops there, but they are not globally minimum. Okay, so one important challenge is when using this gradient descent algorithm is sometimes our optimizer can stop in local minima. Okay, we want to avoid that situation, okay? Wanting to get rich in this global minima. So momentum is the proposed to avoid this type of local minimum situation. And what they do is in this point, at this point, previous formulation was like this. And it can stop there when this goes zero. But in momentum, what they want to do is they are multiplying some values uh, and wanting to add, this VT, this is the previous parameter, and this is the something which is added in this position, okay? And previously, there was no this term in VT. VT is here, right? And that is actually added here, okay? Previously, you can think this part was, there's no this part, then only this, gradient part is added here, right? And V and U and W and B, this is denoting the different parameters, but you can think all of this as sector, okay? Anyways, what they want to add to this part is they just want to add some, this part, they actually want to make it as some new variable, and wanting to, how to say, retain their values, not totally replacing this part as that point gradient. They wanting to somehow accumulate their values here with some ratio, okay? And by doing that, uh, this is somehow accumulating some speed used in previous steps. So if if you add this type of term in the V term here, then even though at this point there this DL sector values are going to zero, but previous this term, they are adding to their current value because doing that, even though their gradient is becoming to zero, they are having some values, okay, here. So mm, I'm not sure you are understanding this. Are you guys understanding this? So previously, this V term is totally composed of this DL sector. And at this point, if this DL sector, which is the gradient, is becoming zero, then it stops there. But this VT is accumulating their previous time value. Then even though their gradient is suddenly goes to zero, they have some value, okay, from the previous value, okay? So they are expressing this type of things like this, use some momentum. So we call this type of accumulated information as the momentum and use this type of momentum to climb up small hill. So this is called as small hill, okay? So using this term, they can anyways go this direction because previously they were going to this direction. So uh, this is similar to real momentum in physics, okay? Right? Physics, there's a term called as momentum, okay? So if some people are going this way and immediately stops, immediately their velocity goes to zero, they have some acceleration to go this direction, go to the same direction. And that way, this momentum is similar to the momentum in physics. Okay, are you guys understanding this? Okay, so you can see this DL dissector is similarly in physics, they can be viewed as velocity, even though they immediately their velocity goes to zero, there's some acceleration. They some push those subject to go that direction that previously goes. Okay, that is called as momentum, and thanks to this momentum, they can avoid local minima. Okay, so previously without momentum, if this DL dissector goes to zero, the parameter, there's no way to escape from that exact that point. But thanks to this M, let's say this term as M, momentum, they are accumulating previous gradient, okay, with some ratio. And thanks to this, they are retaining their velocity, okay? And as a result, they can escape from the local minima, okay? Are you guys understanding this? So these type of small hills, they can climb up using this momentum and then doing, keep going in this way and eventually they can have high probability to reach the global minima. Okay, are you guys understanding this? And uh, and after introducing this momentum, one problem was how to say uh, okay. One problem was um, still, this how to say this DL dissector DL dissector is calculated for old parameters. Okay. I mean, this is not mathematically strict. Okay. So, um, how to say, mm, so this term, we want to think of this as the additional term, but let's I mean we can sorry, we can rewrite it in this way. Okay, so this is some momentum. So without having this VT, okay, without introducing this VT plus one variable, we can directly write this term in this part. Okay, we can do that, right? And we can somehow interpret this as the how to say, this is multiplied term. This is becoming the new parameter and adding this how to say, this part here. Okay, we can think like that. Are you guys following this? And we are somehow adding this momentum in the parameter first and add this gradient term later. We can interpret this in this way, but there's some one mismatch uh, when when we write it in this way. So the parameter W is already added here with the momentum, but the parameter we are differentiating the loss L is not the parameter which is updated. Okay, so here their motivation and the Nesterov gradient descent, they are wanting to reflect this type of things here. So here they want to differentiate their loss respect to the already updated parameters rather than the previous parameters which only have W. Okay. So now in Nesterov gradient descent, they want to get this DL dissector not for old parameter, but want to get this gradient for momentum added parameters. Okay, and this mismatch. So this graph is showing that the parameters are added with momentum, and I mean uh, updated and plus with a gradient obtained for previous parameter. That is the way which is done for previous classical way. Okay, when introduced momentum, their gradients are obtained for old parameters. So this is this thing. But here they are wanting to update the parameters with momentum first and obtaining the gradient for the new parameter which is added with the momentum here. Okay, so by removing this mismatch, this Nesterov gradient descent that is working better, slightly better than the original gradient descent with momentum term. Okay, are you guys understanding this? Okay. Okay. And also there are some more variant in stochastic gradient descent, but you have to understand their motivation, you have to first understand what is the learning rate. Okay, so the parameter sector, as I told you, that is get that is obtained via this formula, gradient descent formula. And we call this epsilon, which is the small value, as the learning rate. Okay. As I told you, in this direction, if parameter is located here, they are getting the slope, which is the DL dissector. And inverse direction of that slope, we are multiplying with small scalar value and update the parameter sector here. Okay. But if that value is becoming higher, becoming larger, so I mean, even this big learning rate, this big epsilon is, let's assume that this amount of big epsilon was used to update your parameter at this time, then the parameter sector will be located here, right? Are you guys understanding this? And also in this part, next iteration will be executed, and that will be actually also the new parameter sector will be obtained this way. Okay. So if these epsilon values are becoming larger, then this formula is not working properly. Are you guys understanding this? That's why we are securing this epsilon as small as possible, like this amount of value, okay? But inversely, uh, if these values are very small, let's assume these values are very small, then it will go very little amount updated from the original parameter sector, right? And it may take a lot of time to converge to this global minima. Are you guys understanding this? Okay. So learning rate, it have to be properly decided. And normally in deep learning, we are starting from here and we see the training curve and adjust this learning rate at the training step. Okay. If this learning rate is too high, it does not converge. Okay. In this kind of situation happens. And if learning rate is too low, then it's very slow to converge. Okay, so we have to properly set this learning rate. Okay, this is showing that kind of problem. So very high learning rate, the loss will, diverge as epochs go. Okay, and if high learning rate, it will not converge anymore after some epoch. So if the epochs go, you have to reduce the learning rate. Okay. So parameters, if they are, you are thinking that if they are not improved anymore, then it is good to reduce the learning rate. Then they can fine tune the parameters. Okay. So in overall training, normally we don't use fixed learning rate. Instead, we are scheduling the learning rate. Okay, so normally at the early stage, we are having the higher learning rate, higher epsilon values. But we are, after epochs go, we are slightly reducing the epsilon value. And there are multiple scheduler already implemented in the PyTorch. And they are very simple algorithm. So they, after some iteration, they are gradually uh, reducing the learning rate size. This is the step error learning scheduler. And exponential learning scheduler, they reduce the learning rate with the exponential formula. So you can search for this and this is the code for that. So if you use this exponential learning rate scheduler, their epsilon values are becoming gradually smaller. I mean, after some epochs, you can also set that epochs. Okay, so this scheduler, you can use this for scheduling this learning rate values. Okay, and also this step error is also gradually removing by, as far as I remember, this is their values are some fixed, maybe fixed. Their offset is fixed, maybe. That's the step error. Okay. Okay. Anyways, you can use this type of learning rate scheduler. Okay. When making the training code. Okay. And this is the how to say naive way to adjust the learning rate. So even with gradient descent algorithm that is having this type of very naive form, you can reschedule. I mean, you can schedule this learning rate via using this exponential scheduler or a step learning rate scheduler. But one systematic way of to scheduling this learning rate is this ADA-grad method. So they are the method that combine the learning rate scheduling with the stochastic gradient optimization. So their motivation is adaptively update gradient for individual parameters. Okay, their motivation is like this. So they are somehow stacking, accumulating the updated information, updated gradient for each individual parameters. So if there's a lot of update happens for some of the parameters, then they want to use the large steps. They retain the high learning rate, high learning rate for parameters that haven't been changed a lot. And they want to apply low error learning rate for parameters that have been changed a lot. So they want to they want to update parameters who haven't changed a lot, but they want to change less for parameters which have been changed a lot. That is the ADA-grad optimizer. So the stochastic gradient descent, we can write it in this way, the new way, slightly new way, the parameters in previous iteration, and this is the new parameter, and multiply epsilon, which is the learning rate, with the gradient at that step, okay? But other grad, their idea is doing the same for this, and even for this, but having new terms in this, okay? Are you guys following this? Only this part is the new thing. And delta means very small scalar value to prevent divide by zero. Okay. When some fraction is divided by zero, then it will give us synthetic error, right, in the code. So this delta is the part for preventing that. But here, this root R is the one we are wanting to use. Initially, R is 0, but they are added with gradient, their square value. They are accumulating this R with their square value, okay? So as a result, this part is somehow accumulating the gradient for each parameter, okay? So if some parameters, they are updated frequently that have larger gamma, larger root R because they are accumulated with gradient that is, enforced to them, okay? But parameters which is not updated frequently, updated less, will have smaller root R. R is accumulating gradient for that specific parameter, okay? So if some parameters are not updated frequently, their gradient were very small. Their accumulated gradient is small, and horizontally their R value will be small. Then this learning rate will be becoming larger because they have small r, their learning rate will become higher than others. Are you guys understanding this? But if R is becoming larger, then their learning rate as a result becoming less compared to others. Okay. So this other graph is doing that kind of thing. Okay. They are accumulating the gradient assigned to each parameter, okay, and adjusting the learning rate for each parameter. Okay. Are you guys understanding this? Okay. But thing is, there's one problem in ADA graph. Okay. If we accumulate these R values with square of gradient, then this becomes saturated fast. So after a few epochs, this becomes already big, and horizontally these values are close to zero. Okay, which means after few epochs, most of the parameters are having less learning rate because they are updated frequently. I mean, updated for few epochs, their scale is already saturated. Horizontally, there's not much update for that parameters. So somehow their scale is, we cannot control their saturation, okay, easily. Their scale, we cannot manage them easily. So the RMS probe is having the same policy, but wanting to somehow, how to say, capture their scale. And these low values are from 0 to 1. So in previous R, they just want to multiply this 1 minus low as the weight to the gradient value and accumulate them gradually by limiting their scales. Okay. So using these very easy tricks, they can secure, the training, problem in the ADA graph. Okay, so that is actually the RMS probe, the new algorithm compared to the ADA graph. Okay, sometimes making new algorithm is easy. Okay, but there's one innovation from here to here. Okay. Anyways, but nowadays we are using ADAM frequently. Okay. I mean, this ADAM optimizer, you can use this SGD optimizer when you train the networks. But nowadays, most of, I mean, researchers are using ADAM optimizer, which is the complete form of optimizer. But basically, they have the concept of sharing the key concept for the SGD. But this ADAM is having the adaptive learning rate consideration and also the momentum things. Okay. So also SGD, RMS probe, ADAGRAD, ADAM, most of things are already implemented in the PyTorch with a one line of code. Okay. So you can just replace SGD to ADAM or other RMS probe or ADAGRAD. Okay. In PyTorch, easily you can change the optimizer, but basically most of them are already based on the SGD. So application-wise, you have to select the optimizer. And I will, maybe this is the last for this lecture. So Adam is the complete form of optimizer, and we are now using Adam frequently. They are jointly consider the learning rate issue and also the direction issue, somehow combining momentum and RMS probe. So their formula looks like this. So basically, their final formula is same as stochastic gradient descent, but having this term, okay, and the below term is similar to the RMS probe. So we are accumulating square of gradient to assign more learning rate for parameters which was not updated before. Okay. And for parameters which was frequently updated, we want to give less learning rate. So below term, we are having the same term, similar term to the RMS probe. But in the above term, here we are having similar things with momentum. So we are accumulating this with some weight. Okay, this is similar to the momentum. Okay, and using updating the gradient as well. So this term is more like the momentum term, and the denominator, I mean this below term, is similar to that of RMS probe. Okay? So this Adam is I mean, more complete form of optimizer. Okay, they are considering learning rate at the same time considering the momentum. Okay, so you may think that this Adam is always good, but sometimes in practice it's not like that. So generally, Adam gives the best solution, but it depends on the application. So mostly we are first try Adam, but if it fails, then we also try other optimizers like RMS Probe or others. Okay. Okay. So this is the end of today's lecture, and later we will also see the data issues in deep learning. Okay. So we will continue that in next lecture. Okay. Thank you, and see you this Wednesday.